All right, I think that'll be good for now. Sorry for the delay. But what we just did was show that this function is continuous at 0. Okay, let me just fill this out right quick for anybody that's not here or that doesn't have the notes. That way you'll have them if you reference them later. Just kidding. I got it oriented again. I thought he had done that, but he did not. That was our conclusion. Anybody have any other questions on that? Okay, so then let's look at another example. This is a graph provided here, and we want to use this figure to determine where the function is not continuous. And we want to use the checklist items to justify our answer. So again, if I say that this function is not continuous at x equals to 3 because there is a jump, while it's technically incorrect, don't describe it like that. Describe it from one or more things from the checklist. Okay. It doesn't matter where we start, so just start listing values of where this function isn't continuous, and then we'll justify the reason it's not continuous. So somebody just start somewhere. At x equals to 1. Function is not continuous at x equals to 1. Why?
Because it doesn't exist.
What doesn't exist?
Where x equals to 1.
Right. Does everybody agree with that? So that's item number 1 on the checklist. The function doesn't exist. Does the limit exist? Yeah, but even if the limit exists, the function doesn't. So there's the item 3 is there's no way for item 3 to be true. Okay, so that's x equals to 1, or else
2.
X equals to 2. Why?
Because the function at 2 equals 3, and the limit equals 1. as it's approaching 2, it equals
Okay, so that means which item is not satisfied?
3.
The third one, good. So everyone see that f of 2 does exist. F of 2 is 3. The limit exists as we approach 2 is 1. But the function value and the limit value are different. So that's item number 3. So we would just say f of 2, the x value, f of 2 is not equal to the limit as x approaches 2 on whatever is this. This is f of x on f of x. Just f. Okay, so that's item number 3 on the checklist. So now it gets a little more tricky because you can look at that graph and clearly see, hopefully, hey, it's not continuous here, 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 and here. So now we got to think about why it's not continuous. So we add just a little bit more complexity to it. Anywhere else?
3.
At x equals to 3. Why is the function not continuous at x equals to 3?
The f of x exists, but the limitation does not.
The function value exists, but the limit as x approaches 3 doesn't exist. Do you all agree with that? The limit doesn't exist there. That's item number 2. The limit as x approaches 3 on f of x does not exist. Why does the limit not exist?
Because it's different on each side.
The limit from the left and the limit from the right are different values. So item 2 fails there. Anywhere else? At x equals to 5. How come?
Because the limit doesn't exist. Well, because there's a
Vertical asymptote?
Yeah, vertical asymptote.
Right, so that's correct. There's a vertical asymptote there, but that's not one of the items on the checklist, right? What item on the checklist doesn't hold here when x is 5?
Well, the function value doesn't exist.
Right, the function value doesn't exist and the limit doesn't exist, right? So just the first thing being false is enough to make the function not continuous. So, I mean, I guess you could really describe it in 2 ways, but it's primarily, the items on the checklist 1, 2, and 3 are sort of nested. If 1's not true, then there's no way 2 and 3, or there's no way that 3 is going to be true, so it's going to fail anyways. So f of 5 does not exist. I mean, if we wanted to, that's fine, I think that's well enough right there. But if we wanted to be a little bit more descriptive, we could say and the limit doesn't exist. So the limit's infinity. Remember from 2-4, that work right there, this right here, all by itself, would tell us that there's a vertical asymptote there. Because as x gets closer to a finite number, the y values get larger and larger. Excuse me, does anyone have any questions on this example? Okay. Couple more examples. So what we want to know are the following functions in 1 and 2, are they continuous at a specific x value or a? So is 3x squared minus 2 over x minus 1 continuous at a equals to 1 or x equals to 1?
No.
No, how do you know that?
Because the moment you apply 1 in, the denominator will instantly go to 0.
Right. If we plug 1 into that function, what do we get? Division by 0, which means it doesn't exist, right? The function value doesn't exist. Whether that's an asymptote or a whole doesn't matter. The function isn't defined at 1. How about function 2? Is it defined if x equals 3 and x equals 4?
No.
No. Anyone on this side of the room want to take a shot at it? What do you think? So we're dealing with a rational function, right? It's a polynomial over a polynomial. When are those functions not defined? Right, it's the same stipulation as always. The bottom cannot be 0. Your function's undefined. We're just going to factor the bottom. Once you factor the bottom, then it's totally clear. 3 and 4 causes the denominator to be 0. So again, this function, not continuous, since both f of 3 and f of 4 do not exist. So it's almost from a purely like algebraic standpoint, you could tell whether or not certain types of functions are continuous or not. So with rational functions, it's just as easy as looking at it through an algebraic lens. What values of x cause me to divide by 0? Those values, it's impossible for that function to be continuous there. Right? Even if you have a whole, the function's still not defined. So even if one of these factors or both of these factors got removed, you still have a whole there. The function's still not defined there. So does that make sense? Does anyone have any questions? Then what we'll see is there's a lot of theorems that follow, but these theorems kind of overall tell us that the functions that we're familiar with are continuous on their domains. And we'll get a lot of theorems that state that. But some of the theorems also deal with how we combine functions as well. Okay. There are exceptions to this. It's not that every function is continuous on its domain. Primarily for us, the exceptions are piecewise functions. Piecewise functions. But functions that you're familiar with, polynomials, rational functions, radical functions, trig functions, inverse trig functions, what we're going to see is that they're all continuous on their domains. And that's kind of justified. It takes a lot of justification to do it. We're just like slapping a theorem down and saying, okay, well, this theorem tells us this, this, and this, and going from there. But so there's a lot of theorems on this page. Continuity rules for polynomial and rational functions are given in theorem 210. Composite functions or compositions, and limits on composite functions. So that's all stated in these different theorems. But theorem 2.9 says that if f and g are both continuous at a, then all of the functions that follow are continuous at a. C is constant, and n is a positive whole number. So what it says is if you've got two continuous functions at a particular point, these operations do not change continuity. You know, the only caveat here is that when we divide, like we saw in the last two examples, you just can't divide by 0. Otherwise f of g doesn't exist. You know, well, I guess we should specify a value, but just like in those previous examples. So I'll just put that, see previous examples. So hopefully that's just still really straightforward. So if I have two continuous functions at a point and I add them, subtract them, multiply them by a constant, multiply them together, divide them, provided the denominator is not 0, or raise any one of them to a power, none of that changes their continuity. So they would still all be continuous at whatever value a happens to be. Does that make sense? Anybody have any questions on that theorem? I don't expect you to know these verbatim, but you should know now, like, you know, if you have to look over this again, that's fine, but you should know that when I perform these operations, it doesn't change continuity unless I'm dividing by 0. Rational functions and polynomial functions. A polynomial is continuous for all x. A rational function, like we said, continuous for all values where the denominator is not 0. So kind of still the same deal here with polynomial rational functions. Continuity of composite functions at a point. So that our composite function, we're f composed of g. F composed with g of x, which is just this thing here, f of g of x. So we're saying those types of functions are continuous when g is continuous at x and when f is continuous at g of x. So those functions have to be continuous on their inputs. And again, basically what that's saying is it's saying the composite function is continuous on its domain. So if you remember how to find the domain for a composite function, then you also know where that composite function is continuous. And so limits of composite functions here are they're just saying that if the functions are continuous, then we're able to pass the limit inside and compute. So yeah, what would be an example? So like an example, just put something concrete to it. For example, if you had to compute the limit as x approaches 4 on the square root of x minus 3. We've seen this before with limit laws, but the formality of those limit laws really wasn't justified. It's the notion of continuity that really justifies a lot of those limit laws. So the outer composition is the square root. We can pass that limit through because it's continuous. X minus 3 is continuous at 4. Or we could just go back and say, x minus 3 is a polynomial function. It's a linear function, but it's polynomial. It's continuous everywhere. It's certainly continuous at x equals to 4. So more or less, the functions above are continuous. Continuous on their domains. Is, I guess, the big takeaway from those theorems. Also, also the idea of a function being continuous somewhere really gives us the why behind direct substitution. Like when we're able to take that limit as x approaches 2 and plug that directly into the function, it's because of the notion of continuity. So we'll mention that too. Continuity gives us the y involved with direct substitution. So like, for example, we'll just write an example out here. For example, the limit as x approaches 2, the function x minus 1 over x minus 4 is equal to 2 minus 1 over 2 minus 4. Since this function is continuous, at x equals to 2. So when we're able to directly plug in with polynomials or any function, it's because the function is continuous there. Does anyone have any questions? So then we're going to kind of shift what we're looking at. And that was all continuity at a single location. We want to sort of broaden that scope and talk about what it means to be continuous along an interval. And there's two things that we're really going to address. The notion of continuity at endpoints, and then once we talk about continuity at endpoints, then we can talk about continuity along an interval. Okay. So here's two examples of different functions, different continuity here. So just visually we can see that this a is included in the function, but the b is not included, and they sort of switched roles over here. A is not included and b is included. So just sort of visually we can tell that, yeah, this function includes a, and it's continuous on this interval. It doesn't include b. A similar thing for the other function. It doesn't include a, but the interval does include b. So we want to look at procedures to make that precise, if you will. We're not always going to be given a graph, so we can't rely on just looking, oh, well, I have an open and a closed circle, it has to be this interval, right? We want to focus more on sort of the algebra behind why this is continuous. Okay. So they're going to call this thing right continuous at A, because, as we'll see in the definition below, this will just kind of solidify it. As I approach A from the right, I can approach A from the right, but I can get right up against it at that point. The parenthesis around B is not only because there's a hole there. Again, we're going to just like throw the visuals out in a minute. But if I look at the limit as I approach B from the left, there's still a limit on both of those endpoints, right? So the reason I'm able to include A, we see that it's a solid point, which means the function value also exists there at A. And we can compute the limit at A from the right. The function value and the limit are exactly the same. So we would say it's continuous at that point. We wouldn't say the function is continuous at the point x equals to b because the function doesn't exist there. So we would say that this is right continuous at A, because A is actually included. We don't say anything about left continuity at B, because it's not, there's nothing really going on there. The situation being reversed over here, this thing is now left continuous at B, because as I approach B from the left, the limit is the function value. So, as we go through some of these examples, I think what you'll see is we'll kind of just look at this through like an algebraic lens. It's much easier for me to determine whether this thing's continuous here to here just because of the domain of the function, or just because of an algebraic procedure tells me that it's true. Unfortunately not. Once we sort of make these things a little bit precise, you need to make sure that we are using limits to justify continuity and not just an algebraic thing. So this notion is illustrated in this definition here for the continuity at endpoints. And so we're saying that a function is continuous from the left, or left continuous at a location at A, if the limit as we approach A from the left is equal to the function value. So it's still the exact same definition of continuity. We've just modified it to fit our particular context. And our particular context is sometimes you deal with a function where you can't use a two-sided limit. So that's the only modification that we've made, right? If you remember our original definition of continuity, we said the function at A has to equal the limit as x approaches A, right? And that was a two-sided limit. So we saw that there's many instances where two-sided limits don't apply, and then that's all we've modified here to talk about when we talk about continuity at endpoints. The function is continuous from the right, or right continuous if the limit from the right as x approaches A is the function value at A. Does that make sense? Does anyone have any questions or comments about that? Also, then we can define what it means to be continuous along an interval. And a function is continuous on an interval if it's continuous at all points of that interval. If the interval contains its endpoints, continuity means that it's continuous from the left or from the right. So, when we say, when you say like the domain is from like -2 to 2, I think it gives it a little bit more meaning as to what that actually means, right? You just say, oh, well, -2 is included in the function and +2 is included in the function. But now what we can kind of we can look at that through the lens of a limit as well. Yeah, the function exists at these values, but also as I approach 2 from the left, that limit is equal to the function value, and as I approach -2 from the right, that limit is also equal to the function value. Okay, so we'll look at a couple of examples to work with that, but initially, do y'all have any questions? And I will say that for sure, like the example that follows here, determine the intervals of continuity. If you look at it from an algebraic standpoint, it is much easier. But in algebra, we never defined what it meant to be continuous, right? Now we're defining what it means to be continuous somewhere. You have to put a little bit more effort and work into justifying something, even if you know that something is true. So we're going to determine the intervals of continuity for this function, but I think now is a good time to take a break. So we'll take 10 minutes. Okay, so looking at that particular function, we want to determine the intervals of continuity. So I guess when you look at that, what comes to mind when you're thinking about the intervals of where that function is continuous. Do any problems jump out at you? Or issues with that jump out at you? So would we just say it's continuous everywhere?
No.
Where might we have an issue on that function?
I'm seeing with the greater than or less than signs.
And that's referencing 0, right? X is less than or equal to 0 for that first piece. The second piece is x larger than or equal to, or larger than 0. So the only issue we may encounter is the continuity at 0 itself. Like everything else, like is x continuous at 1? Is x continuous at 100? Yeah, we know that because this right here, x is larger than 0, includes all x values that are larger than 0. So that function certainly continues at 100 or 10 or 1. The only issue might occur at 0. So we've got to look at the continuity checklist at x equals to 0. Okay, and then we'll look at an easy way, and you might see a really easy way to justify our work. But this is the work that we have to go through will be as follows. So with these piecewise functions, again, those numbers that show up in the domain for each piece are going to be the potential issues of that function. So you've got to look at all of those that show up on those endpoints, basically. Here it's only at 0. So let's answer the question, intervals of continuity second. We'll ask the question, is the function continuous? Is f of x continuous at 0? Does everyone agree that we can kind of rule out everything else? Like the function is continuous everywhere else except possibly at 0? Because every other number is included in one or the other interval. Okay, so how do we know this function is continuous at 0? Well, we've got to go through the checklist. 1, is the function at 0 defined? And if so, what is it? 1. Good. F of 0 is defined, and it's defined as 1. Okay. Then the second question we would ask would be, is the limit as x approaches 0? Or does that limit exist? That's question 2 or item 2 on the checklist. Okay, so in order to answer this question about the limit, what do we need to do?
Pick which one works for it.
Pick which piece it works for, which means we need a one-sided limit. We can't actually compute this two-sided limit without looking at the one-sided limits. Okay. So once we get to item 2, we sort of have to stop and break that apart. Say, well, I can't approach 0 from both sides. Maybe I can, maybe I can't. Just looking at the function as is, we're not completely sure that the pieces are connected. So that's where the one-sided limits are going to come in. So sort of, we'll just call this part 1. Compute the limit as x approaches 0 from the right. And we'll compute the limit from the left. I'm sorry, as x approaches 0 from the left. Okay. And if we go back to, I'm going to back up to our definition once more, reference the definition for continuity at endpoints. Because what we're doing now is we're breaking that two-sided limit up into one-sided limits. And when we compute a one-sided limit and we know the function value at that location, Then we get these notions here, either it's continuous from the left or from the right. So for each one-sided limit, we're gonna stop and say, what does that mean for continuity on the left or on the right? Okay, so the limit as x approaches 0 from the right, which piece do we use? Yeah. So greater than 0, we're going to use the function piece x squared plus 1, and we see that that limit comes out to be 1. So we can compute the other one in a minute, but I want us to stop here and actually discuss what that means for this particular function. We have the limit as x approaches 0 from the right equaling 1, and the function value at 0 equaling 1. So what does that tell us about continuity?
It's continuous.
It's continuous. Yeah, from which direction?
From positive?
Yeah, from the right side of 0. Does everyone agree? This function is continuous from the right. It's right continuous at x equals to 0. So let's just say that here, since the limit as x approaches 0 from the right is equal to f of 0, f of x is right continuous at x equals to 0. Does everyone agree with that statement?
So maybe I'm just missing some obvious here, but if x is approaching 0 from the positives, then won't we be using the other equation, because wouldn't x be over 0 then?
Yeah, larger than 0?
Yeah, so won't we be using 3x plus 5?
Oh, yeah,
I
I
was
didn't,
kinda
I
wondering
didn't verify.
about that myself.
Yeah, I didn't verify. Somebody just said it and I just thought it was right. Yeah, thank you. If we're approaching 0 from the right, we need to use the other piece, the 3x plus 5. Right? Everyone caught that but me, right? All right, good for y'all. Thank you for the correction. Okay, so forget everything I just said. I'm glad you caught that. It means you're getting what we're doing. Didn't catch that. So 0 from the right, 3x plus 5. We've got to use that piece. So this limit, it changes our results. That limit is 5. The function value at 0 is 1. So then what would our conclusion be? It's not
continuous from the right.
It's not continuous from the right at x equals to 0. So we'll write the same similar statement though. Since the limit as x approaches 0 from the right on this function does not equal to f at 0. F of x is not right continuous. At x equals to 0. So if you think about those two figures, when we said that it is right continuous or it is left continuous at A or B, whichever figure we were looking at, all that meant was simply whether or not we're including the endpoint in the interval of continuity. So if it is right or left continuous, that means we're going to have the closed bracket. If it's not left or right continuous, we're just going to have a parenthesis around that number. So if we know this function is not right continuous at x equals to 0, by implication, it's telling us where the function is continuous. So we know this interval, we know where it's not continuous, that means we know where it is continuous, at least from the right. So what this means, that is, f of x is continuous on what interval? Remember, we just computed this limit from the right. And we've now shown that it's not continuous from the right at 0. But again, 0 was like this questionable location. Everything else was totally fine. Here's 0, we've approached it from the right. All of these values are continuous. When we get to 0, it's not right continuous, so we're just not going to include that in the interval of continuity. So f of x is continuous on the interval 0 to infinity, right? So that's the right side of 0. Once we get right up to 0, since the limit doesn't equal the function value, we're going to put a parenthesis around 0 instead of a bracket. Does anyone have any questions on that? So that's one side. We've got to look at the other side as well. So the limit as x approaches 0 from the left, value smaller than 0, we're going to compute the limit on the x squared plus 1 piece. And then we've already done this one. So that limit as we approach 0 from the left turns out to be 1, which means that this limit is 1 and the function value is 1. So we have our statement that is, since the limit from the left is equal to the function value, f of x is what? What would our conclusion there be?
It's left continuous.
F of x is left continuous at x equals to 0. It is left continuous. Left continuous at x equals to 0. So we know what interval this piece is showing us that the function is continuous on as well. That is what we're saying here, i.e. f of x is continuous on what interval? It's left continuous at 0. What interval does that give us? Okay, good. Negative infinity to 0. This time, since it's left continuous at 0, we're going to close that bracket from the left. It's kind of, it's weird, right? We're continuous from the left, but the right endpoint's getting included just because we're coming from the left. It's kind of always that opposite. Anyways, now with both of these limits, we have a complete interval of continuity for this function. And that interval is what we've listed here. Those are the intervals of continuity for that function. So I've run out of room. But we're just gonna say that these are our intervals of continuity. Both of these. So it's a little bit more work to justify that, but notice if we looked at the original definition of that function, we didn't talk about the y values until we computed this limit. We said, all right, well, f of 0 is this particular y value of 1. As we approach 0 from the right, the y value, the limit is 5. but as we approach 0 from the left, the y value is 1. And so that these intervals that we came up with based on the limit gave us our intervals of continuity, and it also tells us that those two pieces are not connected, like they're individual pieces. When we go back up to the function and just look at each piece's domain, we say, all right, well, this function here is defined on this interval in relation to 0, and this function is defined on this interval in relation to 0. So I mean, like, just from an algebraic point of view, we can verify what we've done is correct up to a certain extent. The only other thing from an algebraic point of view we would need to make sure is, are these pieces connected or are they not? And the way we determine if they're connected is if I plug 0 into both of these functions and they output the same y value. They of course don't. Because if I plug 0 into here, I get 1. If I plug 0 into here, I get 5. So they're not connected, just based on that point of view. And we're looking at each piece's domain individually, which consequently is the function's interval of continuity, right? So that first piece, as we approach 0 from the left, we said we can include 0 with our bracket. That's this piece right here. As we approach 0 from the right, we said we don't include 0. That's this second piece right here. So we can sort of verify that pretty easily. However, we do need limits to justify that work, especially when we're talking about intervals of continuity. Okay. So although we could look at this function and just from an algebraic point of view say, okay, well, this is what's going to happen, that's not enough work to justify the question we're trying to answer. So if this is an exam question and you said, and you didn't show any of this work and you just based it off the domain of each piece and said, here are my intervals of continuity, you're going to lose points because you're not justifying anything with limits. Is that clear? Okay. So again, the notion of continuity has to involve limits. Otherwise, you're not really talking about continuity. You're just sort of basing it off of other principles. So are there any questions about that? What's this function's domain? What's f of x's domain? All real numbers, right? Does everybody agree? That function does include all real numbers, but the function's not continuous on its entire domain, right? The issue was at 0, but now we have this, our work, we can say explicitly what those issues were. The issues were I couldn't include 0 as I approached it from the right, but I could as I approached it from the left. Overall, though, however, that function does include 0 as an input. So we've got a similar thing here with function number 2, and we'll look at it the same way. The endpoint here of 1 is the only sort of reason to pause and start to look at what happens at this function at x equals to 1, or as I get closer to 1. So we're basically going to answer the same question here at 1. Checklist item 1, is f of 1 defined? We say, yeah, well, the first piece includes 1, so to evaluate at 1, I'm going to have 1 squared plus 3 times 1, which is 4. So that's the value we're looking at when we compute limits to determine, left and right continuity. So f of 1 is defined as 4. Then we're going to compute the limit in 2 ways. Again, at 1, you've got something goofy happening. You've got to compute one-sided limits. So we're going to have the limit as x approaches 1 from the right, and the limit as x approaches 1 from the left. from the right of 1, x value is slightly larger than 1, we're going to use that top piece to compute the limit. To the left of 1, slightly smaller than 1, it's the second piece, the bottom piece, to compute that limit. All right, so the limit as x approaches 1 from the right, just plugging 1 into the function, we're getting 4. So we see the limit as x approaches 1 from the right and the function value are the same. They're both 4. What does that mean? It's continuous from the right at x equals to 1. Yeah. So I'm just going to put this here that from on this piece 1 and 2 state that f of x is right continuous at x equals to 1. Does everybody agree with that? So we know it's right continuous at 1. This part 1 also tells us what interval this function is continuous on. So what's our interval of continuity? Say that again.
Put 4 to infinity. Oh, I mean 1 to infinity.
1 to infinity?
Yeah, with the 1 bracket.
With a bracket around 1, like that? What do y'all think? If we say it's right, we're saying that this function is right continuous at 1. That's our interval. Does everybody agree?
It's inclusive to 1, right?
Yeah, it includes 1, because the limit as we approach 1 from the right is the function value at 1. Okay? So this limit also equal to 4. So our conclusion in a similar way, f of x is left continuous at x equals to 1. And that means the interval of continuity for this piece interval of continuity is what? Negative infinity to 1 with the bracket, yeah. Negative infinity to 1 with the bracket. So the first example, we didn't really put those two conclusions together because one included and one didn't, right? So we just left it. Here's this interval of continuity and this interval of continuity, making up the entire interval of continuity for that function. However, what would we do in this case?
You just combine them and say the interval is x infinity to positive infinity?
Exactly, right. Does that make sense? So we can include 1 from the left and from the right. It means we include 1. It means that the issue was at x equals to 1. We've determined that we include it from the left and from the right. So we just include 1. So we're just going to put these two pieces together because we can and say that the interval of continuity is negative infinity to infinity. So that's our final answer right there. Does anyone have any questions? Yeah.
For the other one, would we just leave it as the two separate answers?
Correct. Yeah, because we couldn't put those together. Yeah. So the other one, as we left it, is fine. You've just got two different intervals of continuity. Yeah, and just kind of validating that from another standpoint. I don't have the graph for the one we just did, but I think we have a graph here for that first one. So there's that first one we did where we had the two individual intervals of continuity. And then when we look at the graph, that's, it's perfectly clear that our work is what it is, right? We've got this function, we can approach 0 from the left, the function's defined there, but as we approach 0 from the right, the function's not defined there. So we have these two intervals of continuity for this work right here with these two limits from the left and right being the same as the function value just indicates that the pieces are connected. So we've got a piece that's 4, and we've got a piece that's a quadratic. So, it would probably look something like this if we were to graph it. And that was at 1. So let's just say that's 1. So you got an actual point and then a quadratic. So that's more or less what this graph that we're working with, or this function that we're working with, looks like. Any other questions? All right. Next thing is functions that involve roots. So we've got another theorem for that. It says m and n are positive whole numbers with no common factors, which means they're in lowest terms. M and n is like something you can't reduce. So if m is odd, then the function to the n over n power is continuous at all points for which that function is continuous. Again, if m is odd, then this thing right here, m is the denominator, m is odd, so we're dealing with an odd root there. So it's saying that it's continuous at all points for which the function inside the odd root is continuous, right? So if I said the cube root of, if I just said the cube root of x, we would say, well, where is the function inside the odd root continuous? Where is x continuous? Everywhere. It's a linear function. It's a polynomial. It's continuous everywhere. So the cube root of something that's continuous everywhere is also continuous everywhere. In other words, what this first sentence is saying is that odd roots are continuous everywhere the function on the inside of the odd root is continuous. So that's continuous on all real numbers. But if I had the cube root of 1 over x, we wouldn't say that just because it's a cube root, it's continuous everywhere, right? Again, we're basically ignoring the fact that it's well, let me change this to the 7th here. We're ignoring the fact that we're dealing with an odd root and only need to focus on the function on the inside. Okay. This function, just for brevity here, it's not continuous at x equals to 0. The second sentence deals with when m is even, so it deals with even roots. And it says that even roots are continuous at all points for which the function is continuous, just like with an odd root. But it does have this additional qualifier. As with any even root, the function on the inside has to be positive. So the theorem is sort of limiting because it doesn't tell us anything about what happens when the function on the inside of an even root is identical to 0. So it's strictly larger than 0. Sorry, they're using f of a. So what about f of a? Or what about when f of a is equal to 0 is better? So the first thing is to notice that the theorem doesn't include that for us. It doesn't say anything about when the function on the inside of an even root is identical to 0. It's strictly discussing when that function is positive. So in order to determine what happens when the function on the inside of an even root is identical to 0, we have to use the prior methods. We have to test at those endpoints. We just have to test. So it's moderately inconvenient because a lot of it is like that with the piecewise functions, just from an algebraic lens, it seems really straightforward. Like, why should we even involve limits? Again, we have to involve limits because we're talking about continuity, and that's how continuity is defined. So for example, what values of the function square root of 9 minus x squared continuous? So we say, all right, well, we've got an even root. Theorem 213. Theorem 213 states that f of x is continuous when the function on the inside of the even root is strictly larger than 0. So if we can determine when 9 minus x squared is larger than 0, then we have a whole lot of values for where that function is continuous. But again, the thing to remember is that this greater than 0 is the only thing that's guaranteed by that theorem. And so when we get to the endpoints of that interval we come up with here, we're going to have to test the endpoints manually. So when is 9 minus x squared larger than 0? We're just after what x values makes that inequality true. There's a couple of ways to solve inequalities, but the primary one was you first identified when it's identical to 0, because if you know where a function's identical to 0, right, let's say, it's quadratic, so it's a little bit easier, but, if you had these, if you had a function that had those 5 zeros, then you know within this region, in between those two zeros, that it has to be either positive or negative, greater than 0 or less than 0. In this region, you know it has to be above or below, and so forth. So what you did was you found the zeros first, then you just drew that sign chart and tested values to see whether or not something was above or below. So like, do y'all remember that? You had this 0, and this 0. I don't know, let's just say that's 1, 3, and 5. And then what you did was you chose a value in between the zeros, like a 2, and you just plug 2 into the function. And if the function spit out a positive number, you know from in between 1 and 3 that your function's greater than 0. From 3 to 5, let's choose 4, and let's say the function output a negative number, then you know your function's less than 0 there. So do y'all remember doing that? With quadratics, I think it's a little bit easier though, because for the most part, with quadratics, they're pretty easy to graph. We may not know exactly where the vertices are, or the vertex is rather, but you definitely know like where that quadratic, what direction that quadratic is facing. So we know this quadratic is opening down, and it's shifted up 9 units. So this is what our quadratic looks like. All we're interested in is when this thing is larger than 0, and this thing is larger than 0 through here on this interval. So what is that interval? Well, we need to know when it's identical to 0. When does this function equal 0? Here and here. What are those x values? Yeah, positive and negative 3. Okay. So according to theorem 2.13, it says that our function, the square root of 9 minus x squared, is continuous on this interval or when 9 minus x squared is greater than 0, that is when x is in the interval from -3 to 3. From that theorem, you can't include those endpoints, right? Because the theorem doesn't say that this is larger than or equal to. In that case, we would do this, but that's not what the theorem explicitly states. Okay, does anyone have questions on that? So then the next thing, we get a lot of values from that theorem. The next thing we need to answer is, what about the endpoints? So now we're kind of back to the example of the piecewise, when we work on the piecewise functions. We know it's continuous between -3 and +3. Now we're just going to ask, is it continuous at -3 as we approach from the right? And is it continuous at +3 as we approach that from the left, right? So this is kind of like this restricted interval or domain that we have now. And I want to compute the limit as I approach 3 from the left and as I approach -3 from the right. And if those two limits, those individual limits, are equal to the function's value at 3 and -3, then we can close off those parentheses. Okay. So what about the endpoints? We're determining basically two things. We need to compute these limits, but we also need to compare those to the function values from the continuity checklist. So we're going to compute the limit as x approaches +3 from the left on our function, and we're going to compute part 2, the limit as x approaches -3 from the right on our function. So in both instances, what's our limit? As x approaches 3, 0. The limits by themselves tell us nothing. We have to know what's happening on the function itself at 3 and at -3. So then what's f of 3 equal to? No limit here, just straight evaluation. Also 0, yeah, also 0. So what do we know? The limit from the left and the function value are the same, therefore continuous. This function is continuous from the left at x is equal to +3. F of x is left continuous. At x equals to 3. So if we're just taking it a piece by one piece at a time, then what that means is we're going back up to the interval of continuity and say, as I approach 3 from the left, it's the same as the function value. So, you know, from here, we go back up to our interval and say, I can approach 3 from the left, and this parenthesis is now a bracket. And then I'm going to do the same thing for this limit and see what that tells me. Again, we've got the function evaluated at -3 equaling 0, So f of x is right continuous at x equals to -3. And so that those two pieces ask the or answer the question about the endpoints. What about the endpoints? Well, it's left and right continuous at those endpoints. Therefore, the interval of continuity is not the open interval -3 to 3. It's the closed interval from -3 to 3. So then we got to just stitch this together. This and this mean that f of x is continuous on the interval, the closed interval from -3 to 3. So it's a lot of work. We've seen, some of these things are easier to explain, like asymptotes are easier to explain sometimes in an algebraic sense. But then when you make something a little more precise, it does get a little bit more complicated because you've got to use those rules now to show those things. So that's kind of what we're doing here. If you looked at the function, just be mindful when we looked at the piece inside of the function, that was our quadratic. And we were just using that piece to answer, where it was above the axis, right? However, the function that we're actually dealing with, this function that we've determined was continuous on this closed interval, what is this function? What does that look like? Or what is it? So maybe looking at it like this. That's probably not much more helpful, but square both sides. Y squared is equal to 9 minus x squared. Does that help? Add x to both sides. X squared, rather. Does that help? So that is a circle with a center, radius of 3. Center is at 0, 0. So this is the thing, though. That equation that we're dealing with on the very bottom is a circle. This is a circle. Center of 0, 0 with a radius of 3. But we've got to take in context where that equation of the circle came from. If we go backwards and we say solve this equation for y squared, solve this equation for y. So let me back up. If we start with this function as it is and work it this way, we can totally see that it's the equation of a circle. When we work it backwards, however, we would say, all right, well, let me solve for y. Y is actually the positive and the negative square root. But the function we're dealing with is only the positive square root. So the question is do we actually have a full circle 0, 0 with a radius of 3, or is it something else? Notice the function we're dealing with isn't plus minus. The function that we're dealing with is simply when y is the positive square root. When y is positive, so we'll just write that here. This right here is when y is positive. This is when y is positive. So we're not dealing with the whole circle. We're only dealing with half a circle, and specifically the half of the circle we're dealing with is the half when y is positive. We'll just put the circle there, and that part of our circle that's when y is this thing. And the bottom part, that's when y is negative. So if I gave you this graph, we're not thinking about the red part. If I gave you that graph of that top half of the circle and I said, where is this function continuous? You can totally answer that question just by looking at the graph. I know it's the top half of the circle, and I know that these endpoints are included, right? Because that's just when the circle is, or the equation is 0. Nothing like mysterious happening there. But if we were just given that function, you don't need to know what that function represents. You can just work through this limit process and know, what are the intervals of continuity, what's the domain of that function, et cetera, et cetera. But anyhow, for whatever that's worth, there it is. Anyone have any questions on that example? I need to add another page. I got a handout for y'all too. So the other functions that we have, we didn't look at trig functions, inverse trig functions, exponentials, logarithms, and talked about any of that continuity. However, it's just going to be summarized in one theorem. And it's this theorem right here. So it says the following functions are all continuous on their domains. So if we want to know where any of these functions are continuous, then we just have to remember what their domains are. So I'm going to put this in your notes, and I've got a handout for the trig and the inverse trig functions domain. That way you can refamiliarize yourself with those. We do want this in our notes because it takes care of so many functions for us. Okay, so these functions here, I'll just refer back to that handout. Does everybody have one? So that handout lists the domain of those functions. The domain for exponential functions, any exponential function domain is what? What's the domain of 2 to the x? What's the domain of 5 to the x? What? Yeah, they're all real numbers. Negative infinity to infinity. So that's where the exponential functions are continuous. Domain for logarithms, 0 to infinity. We sort of looked at these last time when we talked about the end behavior of both of those functions. So the logarithms are continuous on 0 to infinity. Yeah, if you look at the domain for tangent, cosecant, and secant, and cotangent, they have those k's in there. K is just any integer. It's a positive or negative whole number. So like, for tangent, if I plugged in k equals to 0, then that tells me part of the domain for tangent would be from negative pi over 2 to positive pi over 2. If I plugged in 1, that would give me 1 minus a half pi, so I would have pi over 2 to 3 pi over 2. So k is just a positive or negative whole number. Oops, I kind of went out of order. This really should be after, but I guess it doesn't matter. I guess maybe one other example I want to look at with limits, and there is a final concept in this section. It's a theorem based on continuity that we'll probably look at next class if we have time. So other examples, just one limit. We're going to compute the limit as x approaches pi over 2. And our function is a quotient. The top numerator is 5 times sine x minus 1. And the denominator is cosine squared. So remember, direct substitution entirely depends upon continuity. So when we look at this function, if we say, hey, I know cosine's continuous on its domain, which is all real numbers, but since it's now in the bottom, the denominator of a function, that can't be 0, and I know cosine is 0 at pi over 2, at 3 pi over 2, et cetera, et cetera. We know that this function, we're not going to be able to evaluate this directly. If we plug in pi over 2 directly, then we're going to get division by 0. So then we've got to do a little bit of work here. So direct substitution, let's just write that out. Direct substitution, the bottom becomes 0. What is 5 times the sine of pi over 2 minus 1 become? All of it, or just the sine of pi over 2? Which one were you computing?
No, just the sine of pi over 2, that's 0, right?
1, right. Sine of pi over 2 is 1, minus 1 is 0, times 5 is 0. So remember, in the sense of a limit, 0 divided by 0 isn't 1. 0 divided by 0 isn't 0 either. The top is getting smaller and smaller, and the denominator is getting smaller and smaller. That's all that means. Okay, so then we ask, well, what can we do with this? If the numerator was 0 by itself and the denominator evaluated at 10, right, you're done with that. The answer is 0. Or yeah, the answer is 0. But we've got to now try to get rid of that issue in the denominator, division by 0 in the denominator. There's little to nothing we can do with the 5 times sine x minus 1, but there are many identities for cosine squared. So then we've got to determine, well, which identity would be most beneficial to use. So does anyone remember any identities for cosine squared?
This is 1 minus sine x, 1 minus sine squared x, or something like that?
Yeah.
Is that
Right.
it?
Yeah, remember the Pythagorean identities? That says sine squared plus of whatever plus cosine squared of the same thing is equal to 1, right? And where did that come from? The unit circle radius of 1. Remember, with circles, the radius times the sine value gives you the y-coordinate. So this is like your y. Your cosine was like your x. circle, center, 0, 0, the radius of 1. That's where that came from. So then we can just solve that for cosine squared and see with trig functions, that's always the thing. There's so many ways to represent them. Then the question always is, well, which one do I use? Sometimes it's not straightforward. Sometimes you just have to start with something and then see, does that actually help me? So we're going to start with this identity because that's what was mentioned. We're going to solve for cosine squared and just go from there. Does it actually help us? Okay, so I can write cosine squared as 1 minus sine squared. But the problem is I want to get rid of, I want to get rid of dividing through by 0. So is that going to help if instead of putting this here, I put this here? Is that helpful? Not at least initially. But what can I do with 1 minus sine squared?
Separate out.
Yeah, do you say it again?
Factors of 1 minus sine, 1 plus sine.
Yeah, difference of squares, right?
Yeah.
You gotta keep in mind what we're going for on top. There's no way to cancel the thing on the bottom unless we have it represented similarly to the things on top. So 1 minus sine, 1 plus sine. Is that helpful? Yeah, because it's gonna help us get rid of the sine x minus 1 factor on top with one of those on the bottom. So the thing with trig functions is it's, usually never completely obvious what you're supposed to do. You gotta keep in mind what's on top, what am I trying to cancel, or just in general, what am I working towards? Because initially something might not look like it's gonna work. And you can sort of whittle it down to something that does work. So it's just a trial and error thing. Just when you're dealing with these things, just try to be patient. I would start with the most obvious identities, because rarely are these things like, a double angle formula for tangent or some weird identity like that. They're usually pretty straightforward. Okay, so let's write what we have. We have the numerator here, and our denominator, we want it like this. Okay, so we see that we're almost there. You've got a sine x, a positive sign, and a negative 1. Here we have a positive 1 and a negative sign. So they're not exactly the same factors. However, how do those two factors differ? How do these two factors differ?
Negative sign.
Right, they're exactly opposite of one another. Right? So if, I'm just going to write this off to the side. If we take this factor of 1 minus, this is the other way to look at it, and I factor out a negative 1, then what do I have in parentheses? Yeah. So if I factor a negative 1 out of 1, then that now becomes negative 1, right? If I factor a negative 1 out of the sign is now positive. So if I factor out a negative 1, I have the factor sine x minus 1. We'll go ahead and write that. But I think it's easier just to recognize that the two factors on top, or the factor on top and bottom that we have in green, are just exactly opposites of one another. When they're the same, you cancel them out, you get 1. When they're opposites, you cancel them out, you get negative 1. I think that's an easier thing to remember. So we have the limit. And again, just because we can do all of this doesn't mean it's necessarily going to work for us. It is a little bit more promising because we've gotten rid of something in the denominator. We don't know if we've gotten rid of the issue of dividing through by 0 or not. So we've got 5 times negative 1 on top, 1 plus sign on bottom. So did that help? I don't know. Try to evaluate that limit again, and can we get something meaningful out of this limit? The top is negative 5. What's the bottom? As x approaches pi over 2, 1 plus sine of x approaches 2. Okay, so So that limit is negative 5/2. There might be other ways to simplify this too, but however you simplified it or figured this out, that limit has to be negative 5/2. Okay, any questions on this? All right, I will see y'all Thursday.